if you run the continuous solution, and maybe the optimal one is quite far. So to recap, if you have a continuous problem, you use some gradient. If you have a mixed integer problem, you need to enumerate all the points, and you need to be smart about it. And you can use the continuous solution, so ignoring the integrality of variables, to guide this enumeration. And that means that when you have a continuous convex problem, it's easy. Non-convex is somewhat harder. When you have a mixed integer convex problem, so you are here, it gets harder because you have this exponential explosion of points to look for. When you have non-convex mixed integer, it's even harder because you cannot even use your continuous solution to guide the enumeration. Because if you look at the continuous solution of the non-convex problem, it's harder. It's not. You are not guaranteed to be optimal, so it's more complicated. And here's a list of names that you may find in optimization, just for reference. So another maybe more interesting point is that you can use methods from operation research for data science. It's actually an active line of research, and if you consider the general learning problem, so you have x, which are the features, y the label, theta is some parameter of the model, L the loss function, and this is the risk. So when you learn something, you're actually minimizing something. So it's an optimization problem. And you may translate that into a problem that can be solved efficiently and effectively in operation research. So Jean-François Pouget is an IBM engineer. He's a PhD in machine learning, but he also did optimization in IBM. So he's seen the best of both worlds. And he noticed that in machine learning, often people ignore optimization methods that are from operation research, but could be quite effective. For example, he used Cplex, which is the IBM optimizer for operation research, to solve, to train subparametric machines. And that was way more efficient and effective than the method that you usually use in machine learning. And for example, you can express the linear regression as an optimization problem, where you are minimizing the absolute value of the residuals, which are defined by the difference between the original label and the regression function. I'm not saying you should buy Cplex to do regression or to do data science, because it's a line of research and you need some tricks to make it work, but it's an idea that should work, and so there are really some results in some applications, and so just an idea. Okay. And this concludes the first two sections of my presentation. I now would leave the seat for Alberto. If you have any, do you have any question now?
Yeah. What is the advantages of this Cplex with respect to other standard techniques?
Techniques for what?
For solving the regression problem.
Well, the regression problem in general. Okay, if you talk about data science problems in general, you may have a problem that is not really translatable to operation research problem. But when you can translate a data science problem into an operation research problem, what you get is a better quality of the solution, a guarantee of quality of the solution also, and you can also have an increase in efficiency. As Jean-François Pouget said, he managed to be way more faster than other methods for subparametric machine. So you need some work to translate the statistics or machine learning problem into an operation research problem, but empirically you can have improvement both in the quality of solution and in the efficiency of the solution. Another problem, for example, was about generating correlated vectors. Now, I don't remember exactly the details, but they presented a way by using an open source solver of generating these vectors with a prescribed correlation, with operation research, which was fast enough probably the same magnitude of order of magnitude in terms of computing time, but it managed to be way more accurate and way more satisfying than the heuristic that was used for the in statistics. Now, it depends on how you translate the problem, but in general, you get higher guarantee of quality and more efficiency. Do you have, do you have any problem in mind?
No, I was just, operational research is kind of mainstream field.
Really?
Yeah. What you say right now, I don't want to be provocative, right? It's just an observation from a rookie. Okay, I know. But, it's pretty standard what you say. So why should I use this technique to solve, machine learning problem and get better results?
You shouldn't, because it's an active line of research. So there are no enough, the tools that are going to use operational research are not really ready yet. You can use operational research to solve other problems that cannot be solved or cannot be solved easily with machine learning. But, for example, other problems in machine learning are not yet studied enough to, in operational research, to deliver some improvement about that. I'm not saying that operational research can solve any problem in machine learning. I'm saying that there is some synergy, and by having the two communities collaborating, you can devise some better methods that have huge improvements over the standard ones.
Okay. So basically, the optimization research community is looking for other problems to solve.
Well, we have not other problems.
Other
we are open.
publish.
Both communities are open to collaboration. Let's say.
Okay. Sure.
But, as I said, I'm not saying that you should buy CPLEX now to do that, because it takes. But it makes sense to look at the problem from both point of views.
Okay, I'm not sure, maybe this will be covered later, but in machine learning, unless you work with deep learning, when you're also the solver, the optimizer is a big problem. Two big things you need to optimize are hyperparameters and the feature set, to find the optimal feature set and the hyperparameters. And there's a bunch of techniques that you usually use, but usually they're not very good. Actually, I'm trying to move from random search and grid search of the hyperparameters to Bayesian optimizations. For the feature set, you can try genetic algorithms, wrappers, whatever. But I've never seen something directly coming from operational research, while it's exactly what this field wants to do. Is there something ready to try out when you do something with machine learning, or? Because it seems like you're talking to the perfect strategy. That's the issue you want to solve, but I've never seen an application.
Okay, well, there are some, it depends on, hyperparameter search can be hard to model. In that case, you need to use genetic algorithm or some other search where the model of the problem is quite simple. When you have some more details and you can describe that as a mathematical problem with some equation, etc., then you can try operational search. And that's the rephrasing that is seen here. There are some, as I said, there is an R package that implements the generating correlated vectors that I was speaking about before. There are other problems where maybe you can look at the problem as searching for a parameter, but usually hyperparameter search is I have a bunch of black boxes or gray boxes and then trying to find the best one. So that is, you don't have a model, a problem description that you can fit into a problem description yet. So you need, but there are other problems like clustering, classification, example of machines, where you can easily, well, not easily, you can do that. So it depends on how you can frame the problem. There are some problems where you cannot do anything better than using genetic algorithms or evolutionary programming, because you don't have a strong model where you can use gradients and etc.
So basically, operational research is effective when you can model the problem.
Exactly.
Okay.
Because if you remember the other slide where
you
really
don't
have
need the
data,
model.
you also have the problem description that you can use in the model.
Okay. Okay, thank you.
Yeah.
Is there anything that this distinguished engineer might have said since 2014.
He has a very active blog, and as far as I remember, he hasn't changed opinion about the effectiveness of.
He's still
Well,
confident about implementation of optimization.
yes. When he's confident about it.
Despite the fact that in 2017, for instance, certain frameworks related to deep learning, already dismiss any kind of necessity of modeling or human input, like AlphaGo Zero that learns everything on its own without.
So you're suggesting that with deep learning you don't need to model the problem?
Yeah, it looks like we don't need to do anything. I mean, generalize.
Okay.
Banality, a little bit banal, but
so
2018, 4 years afterwards of his works.
Well, they work on different problems. So yeah, I mean they work on different problems. So there are problems for which deep learning cannot work.
Like?
Yeah.
Like what?
Scheduling, combinatorial optimization, linear optimization. Deep learning works well with unconstrained optimization. When you have constraint optimization and you need to be accurate and you need to know what is the solution, etc. For example, this year and maybe the last year, they presented a few papers about optimization, about combinatorial optimization with networks. The papers were not really well received because basically they were competing with very, how can I say, trivial or old-fashioned ad hoc algorithms for combinatorial problems that also had a particular structure where you could, basically they were, I mean, they could be solved by a greedy algorithm that went into sequence. When you have problems where you need to generate several combinations and you need to backtrack, that is way more complicated. But the other point about deep learning and unsupervised, let's say, optimization is that you are not including the knowledge of your problem into the machine, and that means that you also fail to discover what you don't know about the problem yet.
Or discover something else that might be more favorable for your research. Because there is a possibility to discover something that you have not thought about. Major reason.
In general, when you use Cplex, you optimize something constrained and with specific description, etc. And it also gives you a lot of information. For example, it could give you the optimal price of an additional unit of work, which is not something that and furthermore, inside deep learning there's optimization, and also inside machine learning, but not vice versa.
It's done on its own.
Sorry?
It's done on its own inside deep learning. Any kind of optimization, it's done on its own by the machine.
I'm not sure. Well, my point is that when
optimization is basically learning based on something, and then
it's the other way around.
Based on something that is learned, right? The basic idea of optimization. But in case of deep learning, this kind of optimization is done on its own during the
training.
training.
Okay, but inside the training phase is actually some gradient-based optimization. So it's ADAM, it's conjugate gradient, stochastic gradient descent, and they are used for unconstrained optimization. And they also usually are from the first degree, so you have gradient, you don't use the Hessian. And if you take a constraint problem, so with constraints, etc., and you can translate that into an unconstrained optimization. You just put all the constraint as penalties in the objective function, and that is known to really work badly. It's a very poor approach to optimization because it doesn't exploit all the information about the structure of the problem. So of course, if you have neural networks are kind of Turing complete. So if I have a sufficiently big neural network, I can do whatever I want, including implementing the Russian source optimization. But there are other methods that actually exploit the fact that you have constraints and you need to respect them with. So it's not really easy to, let's say, because the idea of using operational research for data science is that when you have an optimization problem that is for your learning, then the engine, you can change it without changing anything else outside and use another method. But all the previous phases about modeling the data and finding the features, etc., is up to machine learning. What you can improve is the engine side of the optimization.